And thanks for the invitation. My name is Arka Majumdar. I'm from University of Washington, Seattle. And today I'm going to talk about some of the work that we are doing in the field of miniaturizing image sensors using this new nanophotonic technology called dielectric metasurface and some computational post-processing or computational imaging. So I'd like to acknowledge my team and funding who did most of the work. So before I jump into this nanophotonic computational image sensors, let me tell you a little bit about like a broad portfolio of what my group does. So the main physics that we are trying to study is known as the so-called light-matter interaction at nanoscale. Okay? We want to understand how photons and electrons behave if you can put them in a very, very small mode volume and store them for a large amount of time. And to do that, we fabricate, design and fabricate various nanophotonic structures that includes dielectric metasurface, photonic crystal, ring resonator, microdisc resonator. These are generally fabricated with silicon and silicon nitride. And then we put new materials, including 2D material like graphene or transition metal dichalcogenides, complex oxide, phase change material, quantum dot, organic chromophores, perovskite quantum dots on this material platform, on this nanophotonic platform to see can we actually push the limit in terms of energy, power, and the speed. Okay, and using this hybrid platform in my group, we are studying 4 research directions broadly. In one, this we call hybrid integrated photonics. We are trying to see can we actually advance the current state of silicon photonic technology for optical communication, for data centers kind of application. Okay. Then we are also looking into something we call monolithic optical neuron. So we are trying to see can we actually implement a neural network using light, and for that the main technology that we are focusing on is how can we implement the nonlinearity in the optical domain. So the linear part is easy, and I'm going to also talk about a little bit of today, but the nonlinear part, how can we do optically, so we are also looking into that. And if you take this nonlinear interaction between photons, okay, which is generally mediated by light-matter interaction, at a very, very small power scale, so at a single photon start interacting with each other, we can start doing also quantum many-body simulation. Okay, so that's like, these are the 3 ideas that I'm not really going to discuss, but if you're interested, I'll be happy to talk after the seminar. I'm going to primarily focus on this nanophotonic computational image sensors today, and the idea is that if using this nanophotonic technology and some computational post-processing, how can we do imaging in a much smaller footprint with keeping low power and low latency. So that's what I'm going to talk about today. Okay, so why we care? So we all know that the camera is everywhere, okay, and it's going to be even in more and more places. So we know the autonomous transportation, this mixed reality system, they require very good image sensors. This image sensors has to be small, but also has to make this decision very, very fast, consuming very low power. There's also application in smartphone, mobile photography, and also in biosensing. You have to make very, very small optics. Okay. And these really have given rise to an explosion in the field of computational imaging and computer vision, that where you can use small optics or maybe not necessarily very high-end optics to capture information, but then you use computational technique to make a better image. And for computer vision, you want to get more information out of the scene so that you can explain that to a machine. Okay, so there are a lot of work going on there. So let's look at what is the typical pipeline for computational imaging and computer vision. So for computational imaging, the idea is, okay, we have some scene. We want to use a low-end optics. By low-end, I mean it's not necessarily very, like not multiple lenses, maybe a single cheap lens. And we capture something that not necessarily very visually pleasing, but then we turn on computational reconstruction, and you can get a very high-quality image. That's what people are looking into for computational imaging. For computer vision, generally we can use high-end optics because our goal is to capture an image with as high fidelity as possible, but then we turn on our computational blocks. We can extract the features, we can do pattern matching, and we can make a decision. These are very kind of simple building blocks. And I want to point out here this low-end and high-end optics that people are using. Generally, they are made of spherical surfaces, they are made of lenses, and we don't really have control over changing each point of this element. So it's very difficult to like make an optics where we can control like every few nanometers how that surface is going to behave. Okay, so that's what we are doing. Okay. Now, for the computational part, as we all know, that most of this computational has been almost replaced by deep neural network. There has been a lot of interesting algorithm, but over the last few years, as far as I know, the deep neural network has proven to be better than most of this, most of the existing algorithms. So that's what people are using. Okay. So what we are asking ourselves that can we actually use optics, okay, to improve or to reduce the computational load that we have in these computational blocks in computational imaging and computer vision. Okay? And the idea is this, as I mentioned, that we have like some input scene or object, and our goal is to either capture something that's visually pleasing or we have to make a decision. So can we actually engineer an optical system that takes us to an intermediate state, and then we hand off to the computational post-processing software, and the goal is that without this intelligently designed optics, this post-processing software will take much more power and latency. So can we reduce the computational complexity of this post-processing software by using some intelligently designed optics? So that's kind of the premise we are coming up with. Okay? And then the question is, okay, how can we design these optics, the computational design optics? And then you can think about, can we actually co-optimize the optics and computational algorithms together to get to this minimum energy and minimum power? So that's like kind of our big visions as we want to get there. And I'm going to show you some examples to at least make this point that there are certain problems that seems very hard to solve, but using metasurface, using this kind of newly designed optics and computational technique, we can solve these problems, okay? So, and there is some connection with the deep neural network I would like to point out here. So as I mentioned that most of this computational block is actually done with deep neural network. And if you think about deep neural network, what we have, like in a very basic abstraction, we have linear, nonlinear. So the blue is more like linear block. The orange is nonlinear blocks. So you have linear, nonlinear, linear, nonlinear blocks. Okay? It's a very, very crude approximation, but that's what we are doing in conventional deep neural architecture. But can we actually think about putting a significant amount of linear blocks before, and then some nonlinear, or even maybe there are some linear blocks as well. But we are trying to put a lot of linear block in front, and this block we can very easily implement using optics. We don't need to do any reconfiguration. We don't need to do any nonlinear, which is difficult to do in optics. So can we actually implement this first few layers just using optics, a linear processing, so that we can start with a very large image. We can make it ultimately smaller here. Then we hand off to the processing, and we actually need less computational power. So that's kind of the connection with neural network. Okay, but as we all know, the optics are large, bulky, and misaligned prone. So this is actually an image of my labs. We know like there's many, many optics. You have to align them precisely. These are pretty large. So how can we solve that? Okay? And similarly, how can we actually start designing these optics in pretty like almost like the wavelength scale precision? And the answer that we think is the dielectric metasurface. So that's what kind of I'm going to tell you first, that what is dielectric metasurface. To understand that, let's start with something very basic, diffractive optics. Okay? Most of you probably know, but just for the sake of completeness. So when we first time learned about optics in high school, right, we said like we have a spherical surface, light incident at different part of this spherical surface is going to see different curvature. So by Snell's law, they are going to bend by different angle. But another way to model this same lens, this refractive lens, is identifying the fact that light incident at different part of this lens undergoes a different phase shift. And when you think about phase shift, anytime it reaches 2 pi, we can wrap it to 0, and we can get very simple kinoform diffractive optics. It's difficult to fabricate, so what we can do is we can approximate this continuous profile by steps. So either we can do a single step diffractive optics or multi-stage diffractive optics. You need multi-stage because you need to give different phase shift, and the multi-stage diffractive optics generally require multi-stage lithography. Okay? And just, most of you are probably familiar with this, but just kind of want to show you that how it looks like. If this is a lens, the profile is the kind of height, z height, function x squared plus y squared. Once you do wrapping, it's going to look something like this. Very similar to the Fresnel lens. And there is a very, very subtle difference between Fresnel lens and metasurface, in my opinion. So what happens when you do metasurface is you are taking this diffractive optics and putting it in the sub-wavelength scale. Okay? So the periodicity becomes half wavelength, then two things happens. So if you remember basic first time when we learned about gratings and diffraction, that the first order diffraction happens when A sine theta is equal to lambda, where A is the underlying periodicity. But if A is smaller than lambda, then sine theta becomes greater than 1. So that means it cannot happen. So when you have a half wavelength structures, you actually have only zeroth order diffraction. So you can guide all the light to the zeroth order diffraction. You don't lose any light in the higher order diffraction. And secondly, what happens is just by changing the lateral geometry of the scatterer, you can give any phase between 0 to 2 pi. You don't have to change the thickness. So you can fabricate that with only a single stage lithography. Okay? So let me explain that why it actually happens, that why we don't need to use different thickness. So when we first think about the thickness is proportional to phase, right? We are using this kind of equation that the phase shift is given by 2 pi over lambda multiplied by the refractive index multiplied by the length. And to give two different phase shift, we have to use two different lengths. But in this case, we are implicitly assuming the fact that the scatterer size, or if you can think about this material size, the lateral size is larger than the wavelength. But if you make this thing smaller, so for example, we have three scatterer here. All of them are smaller than wavelength, but they have different lateral size. When light hits it, light has a physical extent, and that extent is on the order of lambda. Okay? So light does a kind of spatial averaging of material, of air, surrounding air, and the material index n. So essentially, you are changing the effective index n, and that's how you get the phi. The phase becomes n effective times L. So for the same length, you can give different index, and you can get different phase shift. So that's the qualitative explanation. But of course, to actually calculate quantitatively, we have to run full-fledged electromagnetic simulation, and that's what we do. So we generally start with, we use cylindrical scatterer. Most of the work that I'm going to present here involves cylindrical scatterer because we want to make polarization insensitive imaging techniques. We are not looking into polarization for now. Also, we're doing everything with incoherent light. Okay, and so you can see here that in this structure we have some thickness, some periodicity, and the diameter. So for fixed thickness and fixed periodicity, by changing the diameter, so it essentially boils down to the changing the duty cycle, we can get the phase going from 0 to 2 pi with almost uniform transmission amplitude. Okay, so that's what saying that by changing just the lateral dimensions, we can give any phase shift we want. And you can now think about, like, you can go crazy and start thinking about very, very different kind of scatterer, and you can really start designing the scatterer almost at the epsilon, in the abstraction of diffractive index of the material. We generally don't do that. I'm going to explain why. One of the big reasons is fabricatability. So fabrication of the cylinders is significantly simpler than fabrication of this kind of structure. But it is possible to design the scatterer, and you can get very different phase response depending on how you design the scatterers. Okay, so as I mentioned, so to ultimately design the metasurface, we start with this periodic structure, and we run a bunch of simulations. In all these simulations, we have a fixed thickness, fixed periodicity, and we are changing the diameter. And then we find a parameter where you have almost uniform amplitude, the phase goes from 0 to 2 pi, and something that doesn't have very high aspect ratio, so we can actually fabricate that easily. So these are the kind of three criteria by which we choose the scatterer parameter. Once we have the scatterer parameter, we also need to know that what phase profile we are implementing. Okay? So if we know that this is the ZXY, this is kind of the surface profile we have to implement, we can discretize this surface profile in XY plane. Okay? And in this each XY location, I know what kind of phase we need to give because converting this Z to phase, and then I go here and find out the grading parameters and I put that grading. And this is how the structures generally look like. So it's all these structures that you're seeing, you can see there's an underlying periodicity, it's a square lattice, and the structure and the size of these scatterers are changing, and each scatterer gives you a different phase shift, and that way you can create any kind of phase profile you want. Like you can think about like a rotationally asymmetric phase profile, which turns out to be very difficult to fabricate using diamond turning technologies, but you can fabricate this just using this kind of metasurface ideas. Okay? And the thickness of this structure is on the order of wavelength. So this thickness of this pillar is on the order of wavelength. I also like to point out here, as you can see here, none of them really looks like a cylinder. So this is like SEM of the fabricated structure, but we designed it for cylinder. And it turns out that even when the fabrication is not necessarily perfect, it works pretty well. And it's probably not that surprising because this whole metasurface works by a collective property of all these scatterers. So even if some of the scatterers doesn't work very well or did not come out very well, it still works, the optics still works, which essentially tells you that the fabrication is important, but it's not like extremely, like your fabrication has to be exact. Okay, so the metasurface, these ideas are not necessarily very new. People actually were thinking about this back in like almost 20 years back. They called it sub-wavelength gratings, but these are essentially the same idea. The reason I think there is a huge kind of rejuvenation of this field, there are a lot of work going on right now, is one of the reasons is we have much better fabrication, okay? And also we have a lot of computational power to design these metasurfaces. So some of the designing of these metasurfaces, just using like running these simulations, finding scatter parameter, can take a significant amount of time, and it's probably not possible 20 years back with the computation power we had at that time. So most of these works that we do actually run in the cloud, like AWS, to get the final design for these metasurfaces. Okay. So we use silicon nitride to make our metasurface, and the reason we chose silicon nitride is because this is a material, it's CMOS compatible. We can actually make it in a traditional foundry. We can grow a pretty thick silicon nitride with a very short amount of time using PECVD and LPCVD. So we primarily work with silicon nitride, and of course it's broadband and it works in visible frequency as well. So almost 4 years back, we first fabricated a silicon nitride metal lens that works. We can also make vortex beam generator. We started looking into something called an Alvarez lens. So in Alvarez lens, you actually use two cubic metasurface. You place in front of each other, and when you laterally shift them, you create a lens-like behavior whose focal length depends on the lateral shift. So this is how it looks like. So this is like one Alvarez lens. This is the other Alvarez lens. You place in front of each other, and as you can see, when you sum them up, you are going to see something like lens-like behavior, but your focal length is changing. Okay? And to point out, this is actually a cubic surface. This is like kind of like probably the most simple freeform optics that you can think of, and we can fabricate that with metasurface pretty easily. These are kind of the fabricated structures. We did this experiment. So initial experiments were done by kinematic stages, but now we actually integrated them with the MEMS. We have a comb drive by which we can change this metasurface. We can see this, the comb drive here. So we can now electromechanically tune them. We also have developed some stepper photolithography. So for the large area metasurface fabrication, so you can see this one, my student is holding this pretty large, like almost 1 centimeter by 1 centimeter area, and we demonstrated visible varifocal zoom imaging with this technology. Okay? So now that we kind of understand, okay, how the metasurface is designed in our case, how you fabricate it, so I'm going to tell you about 3 different experiments. Okay? The first experiment is how can we do full color imaging using metasurface. I'm going to tell you what is the problem and how we solved it. Then we talk about computational sensors. And finally, I'm going to discuss that how can we actually start designing this metasurface for applications that is completely different. We have no idea how can we design this metasurface. So there are 3 things I'm going to tell you today. Okay, so let's start with full color imaging. So far all the things that I told you about metasurface, it's ultrathin, it gives everything, like you can fabricate them pretty easily, so everything looks hunky-dory, but what is the problem? The problem is metasurface has very strong chromatic aberration. And it's nothing to do with metasurface per se. In general, any diffractive optics has very strong chromatic aberration. And what happens for metasurface lens, this is actually experimentally measured data for RGB, 3 colors, and this is how the full width half maximum of beam is changing for the lens. So this is, of course, the focal length. So you can see the focal length happens at 3 different points along the optical axis. So what happens then if you actually put a sensor, let's say here, which is well focused in green, red and blue gives you very large spot, so your imaging looks pretty bad. And this is actually how the imaging is supposed to look like if you have a very strong badly chromatic aberration as bad as this diffractive optics. So you have like, this is your scene, you are going to capture something like this. Okay? So how can we solve it? Okay? And this is in many ways is 200 years old problem. People knew from the day one when diffractive optics was working. There are some very recent, very interesting work that came out, sometimes last year. They did something called dispersion engineering. Okay? So instead of the unit cell, in each unit cell, instead of a single pillar, you can start putting more number of pillars. You can change the pillar geometry. The fabrication becomes very significantly difficult because your feature size become much smaller. But it's very impressive that you can actually bring all the color to the focus at the same spot. But it turns out that you're either limited by the area or numerical aperture in this app. And in fact, there is some fundamental limit that people have shown that if you have a 1 micron thickness and your F number is 2, then the highest bandwidth that you can cover at visible frequency is 90 nanometer, around 90 nanometers. So you cannot cover the whole range just using this kind of dispersion engineering for a large aperture or large numerical aperture lens. Okay. It also requires very large parameter search. It's also polarization sensitive, as you can see that this scatterer that this paper used, these are like rectangular scatterers, so you have different X and Y is different. Okay. So how can we solve it? So we, as we were looking into this computational stuff, we thought about, okay, how about this? That we know the traditional metasurface lens is going to give you this kind of bad image. But if you can use a different kind of metasurface, we are not changing the unit cell. Unit cell is still cylinder, but we are coming up with a different design of this metasurface that actually destroys all the color, but they destroys all the color equally and in a deterministic way. So then we turn on our post-processing software to get back the image. So that's kind of what we started with, that can we actually do that? And it turns out that there is an approach that's called wavefront coding and computational imaging. So we are coming from a very nanophotonic background. We did not really know about wavefront coding. It kind of looked like a magic, so there are a lot of things that we are learning as we are working on that. So in the wavefront coding, one of the approach that people have shown that if you add a cubic phase profile with a lens, then instead of a focal point, you create an elongated focal behavior. And what it means is essentially if you have a traditional lens, you get for the focus point, you get a nice looking focus. You go away from the focal plane, you're going to see a large blurry spot. But if you add a cubic surface, you see something that doesn't really look like focus. So that's the penalty we are paying. But it's not different between two different planes. It remains almost same. Actually, people have used it to solve chromatic aberration problem in refractive optics. So there is a paper by Dowski. He showed that you can solve the refractive optics chromatic aberration problem using this wavefront coding. But as you know, refractive optics chromatic aberration is very small compared to like diffractive optics. So we say, okay, can we do that? And what we realized that as we're using metasurface, we really don't need to use two optics. We can just combine them in one surface. We can just add the two optics into one surface because we have subvolume periodicity. We can pretty easily mix this two phase profile. And we essentially designed this, we came up with this phase profile, which is the first part is the lens, and then we add a cubic phase term. Okay? So if your alpha is equal to 0, you get back your ordinary lens, like the metasurface lens. But if your alpha is non-zero, you can see there is some asymmetry that's coming on. Okay? So what happens when you make it asymmetric? So if this is the simulation result. So in simulation, if you have alpha equal to 0, that's a pure lens, you expect to see that this is where the R is focusing, this is where G is focusing, and B is focusing. You put your sensor plane here. So of course, B is green is well focused, red and blue are not. But in our case, we expect to see an elongated profile. So you can put a sensor where all the colors come exactly the same way. Okay? So how does it look in experiment? So in experiment, we put a sensor at the focal plane for green. Okay? And for meta lens, as we expect, the green is pretty well focused. Red and blue looks blurry. But when you use our cubic metasurface, they all looks very similar. Okay? Now, the fact that they all look very similar is very important. Because when you are actually imaging, you are not just capturing a red light, green light, and blue light. You are capturing all the light in between. Even if you use the OLED display, this is not like a single laser-like display. It has some bandwidth. So it's not just these three has to be same. When the camera is capturing, the sensor is capturing, they are capturing all the wavelengths. So they all has to look exactly same. And it turns out they all looks very similar. Okay? But then there's another thing that's very important. So if you calculate this modulation transfer function, which essentially tells you that how much of the spatial frequency from the object is captured in the sensor. If you look at for a metasurface lens, for green, you actually capture a huge amount of spatial frequency and you get a very good image. For blue and red, you capture a very small amount of information and you have a lot of zeros here. Now, zeros are bad because zeros you cannot invert. But in our case, we actually have a large number of spatial frequency that we are capturing, and that's enable us to actually reconstruct the imaging. So there are two things that's important. One is that PSF has to look very similar for all the color, and then this MTF has to have a large amount of spatial frequency components so that you can reconstruct it. Okay? So how it looks, the experiment. So first we did the experiment with red, green, and blue LEDs. And the metasurface sensor separation was 200 micron. It's an f1 lens. So I'm going to just show you this result. So for example, this is captured with meta lens. So green is well focused for the Mona Lisa. Blue and red looks blurry. When you just captured with our EDOF lens, this cubic metasurface, they all kind of look similar, but they all look blurry. And then we turn on our computation, and this is what we get. You can see there is some streaking going on, and I'm going to bring this thing back. The streaking happens because we are using an rotationally asymmetric point spread function. So the point spread function that we have looks like kind of L-shaped. That's kind of the reason we have streaking, and we have some solution that we are still working on. We can actually quantify how good our thing is using the structural similarity factor. So for meta lens, it's around 0.7. Our approach is 0.9, the highest being 1. And I'd like to point out here that the algorithm that we are using is very basic linear deconvolution. Your complexity is order n log n. Okay? And I'm going to bring back to this order n log n number in a bit, because I'm going to show you if you actually start doing something like purely computational imaging, something called this lensless imaging, your complexity is like order n cube. So we are actually benefiting much from using an intelligently designed optics. Okay? So it is the result for white light imaging. An image quality is pretty poor, and I'm going to kind of tell you like some of the stuff that we are doing to make it better. But at least for the tulip, you can see this is the ordinary meta lens. You don't really capture the sky. Your stems are pretty bloody. You start seeing all those things in focus. And like when point out, the stems are yellow. So we are not really working for RGB. We are actually working over the whole visible wavelength range. So we recently extended this concept with addition of this Alvarez idea, and we came up with a new phase profile with a quadric term. And this term essentially allows us to do not just full color imaging, it's full color, but also zoom imaging, in the varifocal imaging. So this is how your point spread function looks like as we have two plates. One is this one, the theta plate, and other one is exactly negative of that. So we laterally displace them. And this is you can see there's an extended depth of focus for all of them, and the central point is also changing. So we demonstrated this imaging with that. So if you do, this is my ground truth. This is how the meta lens looks like. You won't see any boundaries. You can probably see here that there is already some zoom imaging happening, and this is the kind of blow up results. This is how the meta lens works, and this is how our things work. So our image quality is significantly poor. I'm going to show you like how we have improved over last 3 years. So why the image quality is poor? I mean, one of the things is our lens aperture is very small. The lens that we are making is 200 microns. We actually need to make larger aperture lens. We can use better computational imaging algorithm. The linear deconvolution that we are using is actually very kind of rudimentary algorithms. We are now looking into better imaging algorithm. We have a lot of geometric aberrations that we have not corrected yet. So that's something that we are exploring. And also, as I mentioned, for the streaking, we are actually looking into some rotationally symmetric EDOF lens design. Okay? So what happens when we increase the aperture? So the image quality we improved recently. We have a 1 millimeter aperture lens, and to best of my knowledge, that is the largest aperture lens that anyone has demonstrated full color imaging. So there are two lenses. One is a meta lens, and one is this the cubic phase profile. If you zoom it in, that's how the cubic phase profile look like. And this is the image quality. So the image quality, this used to be the 200 micron aperture in 2017. So this is now our image quality is at least visually significantly better. We are trying to figure out how to quantitatively explain that, how to understand the image quality. We are now actually been making bigger metasurface or bigger area. We are trying to solve the geometric aberration using another surface. Hopefully that will improve the image quality even further. We are also looking into other kind of EDOF metasurface which are rotationally symmetric. So this cubic one I told you, but there are like something called shifted axicon, log asphere, also cubic, that can give you this extended depth of focus. We've recently demonstrated imaging with all of them. And overall, the image quality is getting better. It's still not anywhere close to where we can get with our ordinary refractive lens for full color imaging, but we think that image quality is improving, and we have several ways also like better computational algorithm that I mentioned to get image quality even further better. Okay? But the main point that I wanted to point out here, that using this computational algorithm, it is possible that to solve this chromatic aberration, but the price you pay that you have to do computation. It's not like there's no free lunch, essentially. Okay, so let's talk a little bit about this computational sensors. That can we do anything other than this full color imaging? But before that, let me kind of motivate this, that what we actually have done, like in a kind of a bigger picture. So for most of the nanophotonic, most of the image sensors that we are using, we want to have lower power and smaller size. That's kind of the holy grail, to put like more sensors in your, maybe your augmented reality visor or your cell phone. Okay? If you use an ordinary lens-based imaging, that's what we're generally using, your size is larger, okay? But your power consumption is pretty low. And in this case, we are talking about power consumption as extra power consumption that you need, not the sensor power consumption, because that you always need to kind of just collect the data. If you use lensless imaging, that's like another paradigm where a lot of computational imaging people are working on. They actually use kind of more like a random surface. You capture, but you know exactly how that surface works. You calibrate it beforehand, and then you do this some kind of regularization and some kind of optimization. The complexity there is order n cube. So you actually can make very, very ultra thin sensor, but your computational complexity is order n cubes. You need more power and more latency. And where we came is somewhere in between with this. Right? We think that we still need to place it a focal length apart, but we make our optics very thin. Our focal length can also be small, but there is some requirement. It cannot be like as thin as you want. But then we lose some information like color. We get back the color putting this computational algorithm, and that complexity is ordered in n log n, so it's significantly lower. But we want to go somewhere here. And that's kind of where we think the computational sensors might play a very important role. And I'm bringing back the same slide again. The idea is, can we start designing these optics, and can we start designing this algorithm together to get to that point? So I'm going to show you one example that we have recently looking into, something called for depth sensing or for 3D imaging. And the idea is that if we have an optics that creates a point sweat function that doesn't change with depth, we can design that. This is essentially our extended depth of focus lens that I mentioned before. So this point sweat function remains same between 10 centimeter, 20 centimeter, 50 centimeter. But then we can design another optics where the point sweat function changes very rapidly. So this is actually known as a double helix point sweat function. This is, again, it was known in the traditional macroscopic optics community. We are trying to bring it in the metasurface. And the idea is we actually have two spots, and these two spots rotate depending on which plane you are in. So you can actually use this plane as a calibration point because it's not changing. And from there, you can figure out, okay, what is the point sweat function from the captured image, and from there you can get the depth. As I mentioned, this was known. People actually have looked into this, but this is what people have done before. This will work. So this same approach required like multiple lenses and a special light modulator. The special light modulator actually used to project two different kind of phase profile. One is cubic and one is the double helix, and you need multiple 4F kind of system. So it's a pretty big bulky system. Now, metasurface allowed us to collapse everything to a single surface. So that's how the whole thing looks like. So we have two surfaces. One of them here is actually this cubic one. It's a lens plus cubic, and this one has lens plus this double helix point sweat function. And of course, if you zoom in, you are going to see this the scatterer. So when we capture it, it's probably not very clear. So we're actually capturing UW here, but from there, we can bring this U and W to focus, and we can also get the depth information. Now, there is a little bit of catch, as you can see, that there are like two optics. They are not exactly placed in the same optical axis. Like if you're doing SLM, your optical axis remains same, but now they are slightly different. So we have to change the computational algorithm a little bit. And if you don't do that, this is the depth you are going to get, the circles. But ultimately, with this our new computational algorithm, which is detailed in this paper, we can see that all the lines actually, we can estimate the correct depth. Okay. So this method that I was showing is shown to be better than just using simple depth from defocus problem, just if you're using a single lens from an information theoretical perspective. And we actually can reduce the volume significantly compared to like what traditionally exists using this metasurface approach. So what else we can do? So right now we are actually looking into the whole pipeline of this imaging. So we actually created a multi-scale electromagnetic model for this optical image formation using metasurface. And then we can add like noise that we are having from the camera sensors. And then we can also add a block or computational pre-processing where we have trainable filter parameters. So for Wiener filter, we generally use the SNR ratio, but we can use other kind of filters, including a neural network. And we train this whole network. We put image, and for the metric is essentially the same image coming out, I mean, for this particular problem that we are solving to improve the image quality. And then we code them in TensorFlow, and we actually train them to get the metasurface parameter, and we also get the parameters for this computational post-processing. So there is a little bit tricks. We actually have to implement this electromagnetics problem in TensorFlow because each stage has to be differentiable. Previously, what we are using is a lookup table that's not that easy to implement, use in TensorFlow directly. So these kind of some of the initial simulation results. So if you don't use just an ordinary optics, no deconvolution, this is how it looks like. When you use the optics and we just add some deconvolution, these parameters are not actually co-optimized with the optics. This is how the image quality looks. And then when you do final, essentially means we co-optimize the optics. We are changing the surface as well as we are changing the computational algorithm together. So this is how the image quality looks like. So we are actually working on that now, doing an experiment and see whether we can actually improve the performance. We can also start thinking about object detection with this metasurface, kind of more like metasurface front end and computational back end. So one of the approach that one of the problem that we are looking into is this handwritten character recognition from MNIST database. And we actually put like several of the diffractive optics. Okay? And this work is very similar to a work that came out in science very recently in the terahertz domain for, they call it diffractive neural network. I'm going to tell you like what is the difference. So we are actually not just doing optics, but we are adding then some electronic layer as well. So we are actually using another fully connected layer. But by the time this image comes here, it's much smaller image than when we started with, and a hyperbolic tangent nonlinearity. So if you don't use that, we can actually get up to 90% accuracy from MNIST database. But it turns out that once you start adding some noise, we basically, the noise is that each of the scatterer that we are making, it has a 10% fabrication error, which is going to be happening for optics. So I think that's kind of a big difference between terahertz and optics. In terahertz, everything is much bigger, so you don't really need to incorporate this kind of fabrication imperfection, but for optics, we have to. Once we do that, our computational accuracy goes down significantly. But then, if we add up this computational backend, we can get up to 90% accuracy. Okay? And we very recently also fabricated this structure. We used the nanoscribe 3D printer, so we can 3D print all these optics on top of each other. We have like a 5-layer optics, and we are kind of testing. We're just showing one surface because we cannot really do SEM of multiple different surfaces, but we can actually fabricate a stack of these optics, and we think that we can actually use it for also object detections. We are testing this. Okay, so far all the optics that I told you is kind of we already knew beforehand, and then we are implementing the metasurface. Can we actually come up with new optics completely? Yeah. So that brings me to the last topic. And if you look at this problem, there are two inverse design problems that we are asking. One of them is, given an application, how do we identify the desired phase distribution? So this cubic profile or double helix, we already knew. We just implemented that. But if you don't know what is the phase profile, how can we get this phase profile given a particular application? And then, given a phase distribution, how do you identify the correct distribution of pillars? So when we are actually, I was explaining this before, that how we do our experiment, how we do our design, I kind of glanced through it. I did not really explain very details, but we do something called local phase approximation. So we are assuming a whole grating structure behave almost like a single scatterer. And this is a kind of a good assumption as long as light is well confined in the scatterer. But that may not be the case, or if your gradient is very high, this kind of assumption falls. So just because you have a phase profile and you discretize and you find the scatter parameters, it doesn't really work very well. So given a phase distribution, how can we identify the correct distribution of pillars? That's like another problem. So we really need to solve the whole electromagnetic problem for the whole structure. We cannot really solve for unit cell engineering. That's what kind of it boils down to. So to solve that, very recently we came up with an idea based on me theory and adjoint optimization. So as I mentioned, that we need to solve this whole structure, whole metasurface, And if you want to do like full FDTD, it takes like significant amount of time. It probably takes like few days to just get like one design out. So we use a me theory, which reduces the complexity significantly. So the way it works, we start with our initial condition. In this case, we make all the scatterers same. We run this forward problems. We solve this whole structure. And this is the step that's expensive computationally. If you want to do full FDTD, we solve it using me theory. We calculate the figure of merit. The figure of merit is basically what you want to optimize. Okay? Then we do the inverse problem. So essentially, we calculate the gradient using adjoint optimization, and then we update the scatterer. Okay? Now, as we are using me theory, we are currently limited to either sphere or ellipsoid. We cannot really do it for cylinders because the me theory kind of doesn't really give you that much benefit. If you're doing the full cylinder, it becomes almost like an electromagnetics problem. But for sphere and ellipsoid, you can actually get significant amount of speed up compared to just full FDTD. So we first wanted to make a lens. Okay, so the lens is like we want to put all the power here at this point, and we started with the uniform array of sphere. We optimized it, and we get back the lens. So this is theory works. It just shows that it works. But lens you already know how to make. So what is the point of doing that? So we wanted to do something different. So one of the idea we had is we wanted to solve a toy problem. And the problem is that I want to make an optics that's going to focus light in one plane. In the next like few micron apart, it's also going to focus, but in different X-ray location. So you are going to create a focal point that is following an helical kind of beam shape. That's how as you go the optical axis. So we actually wanted to solve this problem. So we chose 8 per plane, and in each plane we identify which one is the brightest spot. But if you just put only the optimize the bright spot, it turns out it's actually not a very well-defined problem. So we also had to put some dark spots. In this case, the dark spots are essentially telling you the 2 surrounding plane, wherever there were bright spot before, now we have a dark spot. Okay? And this is actually being some kind of an interesting realization for us that how do you design this figure of merit is non-trivial. And I think there requires a lot of intuition from optical engineers to figure out how to design this figure of merit if you want some optics to work in a certain way. Like one of the kind of trivial figure of merit you can think of, why don't we discuss the whole plane? We can basically say at each plane, put everywhere at 0 except 1 point. But then it gets way too complicated and it doesn't really work. It also gives you kind of bad results. So this is kind of, there is some kind of a hit and trial involved to figure out the figure of merit. Anyway, so we put this problem to our computer, and it spits out this structure. So it essentially gives me a structure. It looks kind of random. There may be some remnant of lens that you can see, but it's a fairly random structure that this computer spits out. Then we can run the simulation to see how it's supposed to work. So you can see the brightest spot that we are seeing is actually changing the XY location. This is along the optical axis. You can also see that the point where we wanted to make it 0, it's actually trying to make that 0. So it's not quite perfect, but at least it's going towards a solution. So then we fabricated the structure. So as I mentioned that we are making sphere, right? Because we cannot make cylinder. So sphere you cannot make with lithography. So we have to do 3D printing. So we use nanoscribe to fabricate the structure. And this is how kind of the zoom in looks like. So the way this nanoscribe fabricates it, they essentially create some pancakes kind of structure, but each pancake has varying diameter, and that's how you make a sphere. And of course, you cannot make a full sphere because sphere doesn't have like any contact area, so that's going to fly off. So you have to make like almost like 80% sphere, and then we just have a base. So we used that, and we did this experiment at 1550 nanometer. So we did get these bright spots that's changing, and if you track this bright spot and place it on a circle, you can see they match pretty well with the theory. Whatever we expect the theory, we can actually get that in experimentally as well. Now, why it is important? Because now we have a tool to do point-state function engineering. So previously, this double helix function that I was showing you, that came from like our knowledge, previous knowledge. But if you can start thinking about any arbitrary optics, arbitrary point-state function, there is a tool at least that we can use to start fabricating, start predicting some interesting design. Of course, there's a lot of work that needs to be done. One of the things is better computational method to accommodate arbitrary shape of scatterer. This is not arbitrary. You can do only sphere. We can do arbitrary radius of sphere, but it has to be just sphere. Secondly, the figure of merit engineering. The figure of merit engineering turns out to be a very, very non-trivial problem. We don't have a prescription of how to do that. It's kind of more like hit and trial. And I think there is a lot of interesting math that can be done to figure out how to do this kind of optimization. We're also looking into some other inverse design, including topology optimization in collaboration with Professor Stephen Johnson at MIT. And we recently demonstrated an extended depth of focus cylindrical meta lens. So we make a cylindrical lens that has the ordinary cylindrical lens based on our known phase profile and then we use topology optimization to fabricate this design a new structure. And as you can see that your focus is like not like the red one is ordinary lens and the blue one is this elongated depth of focus. We estimate we have almost 2.5 times enhancement of this extended depth of focus. It's not good enough to do full color imaging, but at least it shows that the inverse design gives us some way to make optics that doesn't really normally exist or we don't have very good intuition for. Okay, so in summary, I told you about this full color imaging. So I think there is a way to solve this chromatic aberration problem in metasurface using computational imaging algorithm. There are, of course, room for better computational algorithm, but we can also use the same techniques to do zoom full color imaging. And we don't have any limitation on the aperture, or at least up to few centimeter, we don't envision any problem. But if you want to make it like a meter or some very high optics, that's a different problem, I think. We also show you some results on the depth sensing. So that's an example of computational sensing, but I think we can push this technology to start looking into passive object detection and co-optimize the metasurface and computation algorithm to get like both power and speed benefit. And finally, I tell you a little bit about this inverse electromagnetic designs. We are looking into this me theory and adjoint optimization, but right now we're also exploring some neural network, and there are many other groups who are looking into deep neural network as well. So essentially, I like to kind of end that this computational sensing really opens up a new way of thinking about optical computation. Like essentially doing a linear computing with this optics to get to intermediate space so that your overall energy and power, energy and latency is minimized in some way. And I would like to point out that if you are not limited by energy and speed, then this is not going to give you a better solution than using a high-end camera and walls-based deep neural network to find doing computer vision. So this is really when you have constraint from size, power, and latency. That's when I think some of these things are going to be very useful. So thank you.